Hello, Thermodynamics students. For this week, we're going to be getting into the concept of entropy from chapter 7 of our textbook. And these are going to be some example problems we're going to go through, and then we'll go through the answers as well. And within our textbook, we have some charts that we're also going to be using in order to figure this information out as well. So, going to the first problem, during a reversible process, 25 kilojoules of energy is removed from a system at a constant temperature of 400 Kelvin. Find the entropy change for that system. Well, for problem 1, the change in entropy is equal to the change in heat divided by the temperature. So delta S equals delta Q over T. 25 kilojoules were removed from the system. The direction of heat is usually considered the positive direction is going into a system. Therefore, if we're talking about change in heat, if it's leaving the system, we assign it as a negative sign. So negative 25 kilojoules of heat divided by 400 Kelvin gets us our answer of negative 0.0625 kilojoules per Kelvin. And this would be the official unit for entropy, a unit in terms of energy per temperature. Now, question 2. During a reversible process, 60 kilojoules of energy is added to a system at a constant temperature of 380 Kelvin. Find the entropy of the system. Well, the key word here in this case is that energy is being added to our system. And we're going to assume that that is heat energy. So the change in entropy, delta S, equals change in heat, delta Q, over temperature in Kelvin. Because that 60 kilojoules was added to our system, and the direction of going into the system is the positive direction for heat, that is going to be assigned a positive sign. So 60 kilojoules per 380 Kelvin gets us the answer of positive 0.158 kilojoules per Kelvin. For problem 3, during a reversible process, a system at a constant temperature of 350 Kelvin has an entropy change of 0.12 kilojoules per Kelvin due to heat transfer. What is the heat transfer to this system? All right, this just involves rearranging our equation from delta S equals delta Q over T. Well, delta Q is just the temperature times the change in entropy, T delta S. Therefore, 350 Kelvin times 0.12 kilojoules per Kelvin. Kelvins cancel, we're left with 42 kilojoules of heat transfer. Now, we're going to get into our next problem. Question 4. Question 4 says, mixing of the fluid in a rigid system generates 0.09 kilojoules per Kelvin of entropy. What is the heat transfer? What heat transfer is required to maintain the fluid temperature at 520 Kelvin during the mixing process? Well, we're given entropy and we're given our temperature. Now, for this, think of mixing as a source of friction. Heat will need to escape the system in order to maintain the temperature. Now, heat transfer equals temperature times the change in entropy. 520 Kelvin times 0.09 kilojoules per Kelvin gets us to a heat transfer of 46.8 kilojoules. Now, the positive direction of heat transfer is heat energy entering a system. Because this system is generating friction, which is going to be generating heat internally, that heat must transfer out of the system in order to stay at 520 Kelvin. So that's why as the generated heat transfers out of the system to maintain temperature, our answer is going to be negative 46.8 kilojoules for our heat transfer. And again, that's why we have a negative sign. Negative 46.8. Now, question 5 says the isothermal heat transfer of 54 kilojoules of energy occurs from the system at 450 Kelvin to the surroundings at 300 Kelvin. For an isothermal process with no internal irreversibilities, find the change in entropy of the world, that is, the system plus the surroundings. This is going to involve a few separate steps. First off, we're going to need to calculate the entropy change for the system. Now, delta S of the system, SYS, that is going to be 54 kilojoules, negative 54 kilojoules, divided by 450 Kelvin. As we reread the problem, that is 54 kilojoules that goes from the system to the surroundings, so it is leaving the system. Because normally we think of the positive direction of heat transfer as going into something, because it is leaving the system, that's why we assign it as negative 54 kilojoules per 450 Kelvin. This gets us negative 0.12 kilojoules per Kelvin. Now, the entropy change of the surroundings. Because that 54 kilojoules is entering the surroundings, we keep it as positive. And the surrounding temperature is 300 Kelvin. This gets us a change in entropy for the surroundings, SUR, of 0.18 kilojoules per Kelvin. So the global entropy change, or the world entropy change, is going to be the entropy change of the system plus the surroundings. So delta S of the world, or globally, that will be negative 0.12 kilojoules per Kelvin plus positive 0.18 kilojoules per Kelvin, or overall 0.06 kilojoules per Kelvin. Now, we're going to look at question 6. Question 6, what is the change in entropy of 2 kilograms of air during a reversible isothermal compression from 350 kilopascals of pressure to 400 Kelvin of temperature and 600 kilopascals of pressure? If necessary, our gas constant, universal gas constant R, equals 0.287 kilojoules per kilogram Kelvin. The isobaric heat capacity for air, CV, is 0.718 kilojoules per kilogram Kelvin, and the isochoric heat capacity, CV, equals that value. And the isobaric heat capacity, CP, equals 1.005 kilojoules per kilogram Kelvin. Now, let's look at this process. It's an isothermal process, so the change in heat transfer equals the change in work. Going through our ideal gas law, PV equals nRT. Well, or in reality, PV equals mRT. Regardless, during this type of process, the amount of substance, the gas constant, and the temperature are all kept constant because it's isothermal. T is a constant. That means that PV under the initial conditions equals P times V under the final conditions. Rearranging our ratios, the initial pressure divided by the final pressure equals the final volume divided by the initial volume. So going from our prior equation for work, that was pressure times volume, initial pressure times initial volume equals the natural log of final volume over initial volume. We can replace this ratio V2 over V1 with P1 over P2 based off of the simplification we just did. So instead, work equals pressure times volume, initial pressure times initial volume, times the natural log of initial pressure over final pressure. Those are just two options we can use. Now, for initial volume, we're going to solve that through our rearranged ideal gas law. PV equals mRT, M for mass, so mass times R times T divided by P for pressure. The initial volume is 2 kilograms times 0.287 kilojoules per kilogram Kelvin times 400 Kelvin divided by the initial pressure, 350 kilopascals. That gets us an initial volume of 0.656 cubic meters. Because, again, we're working with isothermal processes, the heat transfer equals the work change or work transfer, which would be 350 kilopascals, the initial pressure, times 0.656 cubic meters, the initial volume, times the natural log of P1 over P2, 350 kilopascals over 600 kilopascals. And that got us to negative 123.754 kilojoules of heat transfer. The reason why we did this rearrangement of ratios from V2 over V1 to P1 over P2 is because in our problem, we're not given the initial and final volumes, but the initial and final pressures. So basically, instead of solving for V1 and V2, let's just solve for V1 and then plug in P1 and P2 because we're already given both pressures. Now, as always, our main equation is the change in entropy is the heat transfer divided by temperature. So a change of negative 123.754 kilojoules divided by 400 Kelvin equals negative 0.309 kilojoules per Kelvin. For question 7, the question is, what is the change in entropy of 2 kilograms of air during a reversible isobaric compression at 350 kilopascals from 640 Kelvin in temperature to 400 Kelvin in temperature? So isobaric, our pressure is what is constant during this particular process. So, under isobaric processes, the change in entropy, or delta SP, P for isobaric pressure, can be set equal to the mass times the isobaric heat capacity, Cp, times natural log of the final volume over the initial volume. If we go back to our problem, we're not given volumes, but we are given both initial and final temperature. So PV equals nRT. Really, that should be PV equals mRT for mass. Well, M, R, and P are constants. So if we rearrange them, we have V over T equals NR over P. So V1 over T1 equals V2 over T2. And if we rearrange these so that we have our original ratio V2 over V1 on one side, that can be set equal to T2 over T1. So solving for isobaric entropy change, that would be the mass of 2 kilograms times 1.005 for kilojoules over kilogram Kelvin times the natural log of T2 over T1, or 400 Kelvin over 640 Kelvin, and that gets us to negative 0.945 kilojoules per Kelvin. So questions 6 and 7, really that's just practicing how we can use our ideal gas law to take an initial ratio of parameters we have used in the past and replace them with values that we already have. In this case, for question 7, we were already given initial and final temperature, not initial and final volume. So we just rearranged our volume ratio to our equivalent temperature ratio. And that was good practice. Question 8. At 1 megapascals of pressure and 500 Kelvin, water expands to 100 kilopascals in a reversible adiabatic process. Now, volume and pressure are inversely proportional, so by expanding its volume, its pressure decreased. What is the quality, chi, of the mixture at the end of this process? And we're going to need our tables for this problem. Well, let's look at what we're working with. For table B2, we're going to look for 0.1 megapascals, or in other words, 100 kilopascals divided by 1,000. So we're going to look for 0.1 megapascals, and we're going to find that the specific entropy for the liquid is 1.3028 kilojoules per kilogram Kelvin, where for the vapor, the specific entropy is 7.3588 kilojoules per kilogram Kelvin. So again, table B2, looking at our pressure of 0.1 megapascals, S for the liquid, 1.3028, S for the vapor, 7.3588. That's because in our question, water expanding in a reversible process, we're going through table B.2 for our saturated liquid and saturated vapor parameters. Now, if we look forward, in table B.3i, we are looking at the total entropy. That would be 6.825 kilojoules per kilogram Kelvin. Now let's look at our values. Table table B.3i, we are at 1 megapascal pressure, like what we were at the start, and we're looking for 500 Kelvin. So that would be, for the total specific entropy, 6.825 kilojoules per kilogram Kelvin. All right. So what we have here is our mass times the total specific entropy, SP, equals the mass times our quality chi times the vapor component of entropy, plus the mass times 1 minus chi times the liquid component of specific entropy, plugging in our values of 6.825 kilojoules per Kelvin, kilojoules per kilogram Kelvin times 1 kilogram. I'm just going to skip to where multiplying by 1 kilogram gets the kilogram in the denominator to cancel out. So what we're at now is 6.825 kilojoules per Kelvin equals chi times 7.3588 kilojoules per Kelvin plus 1 minus chi times 1.3028 kilojoules per Kelvin. And if you just plug this entire equation into Wolfram alpha and just replace chi with x and ask it to solve for x, it will tell you that x equals 0.912. So chi equals 0.91 or 0.91. And that would be our quality. For question 9, what is the change in entropy of a 3 kilogram steel ball where its heat capacity is 480 joules per kilogram Kelvin? And during that process, it is heated from 300 Kelvin to 720 Kelvin. All right, a pretty straightforward equation. In general, the change in entropy is the mass times the heat capacity times natural log of the final temperature over the initial temperature. So we're given all those values. Change in entropy equals 3 kilograms times 0.480 kilojoules per kilogram Kelvin times the natural logarithm of 720 Kelvin over 300 Kelvin. That gets us to 1.26 kilojoules per kilogram for our change in entropy. And lastly, question 10. An isolated system includes 0.5 kilograms of air at 300 Kelvin and 400 kilopascals in a closed chamber. A secondary chamber is initially evacuated or emptied as shown. We have our primary chamber, our initial chamber with our air, and a secondary chamber attached to it that has no material, no air in it. And these are currently separated. When that separation or partition between the two chambers is removed, the air expands to fill both volumes, so the entire volume of both chambers, and the pressure drops to 180 kilopascals. By the volume increasing, pressure decreases. It decreased to 180 kilopascals. Find the change in entropy of the air during this sudden expansion, and necessary isobaric heat capacity CP is 1.005 kilojoules per kilogram Kelvin for air, and the universal gas constant is R equals 0.287 kilojoules per kilogram Kelvin. Well, during this transition, the change in entropy can be set equal to the mass times our gas constants times the natural log of our initial pressure over our final pressure, P1 over P2. Using the values that we were given, change in entropy equals 0.5 kilograms times 0.287 kilojoules per kilogram Kelvin times the natural log of 400 kilopascals divided by 180 kilopascals. Kilograms cancel. Kilopascals over kilopascals Kelvin. It's just kilojoules per Kelvin. Acceptable units of entropy change. And our value or magnitude is 0.115. So the change in entropy for that sudden transition is 0.115 kilojoules per Kelvin, I should say. Kilojoules per Kelvin. Yeah. Pleasure to have you all in class. The main areas where students have gotten errors is n- not being comfortable with these replacements for values in parameters, such as changing our volume ratio to pressure ratios or temperature ratios, depending on the values that are already given, unless you want to try to do it the long way and solve for each value if it's not already given. Understanding the direction of heat transfer. For example, if the heat transfers into a system, we make that positive. If the heat transfers out of a system, then our correct answer would have a negative sign. And that also affects how we calculate our entropy transfer, change in entropy. And lastly, some equations that can be tricky, such as when to have entropy equaling mass times heat capacity or mass times the gas constant. And those can vary depending on if we're isobaric, isothermal, isochoric, adiabatic, things like that. Just to make the subscribe button look interesting, if you would like, you may subscribe to the channel. If you want, you can also like the video as well. But it was a pleasure to work with you all on this lesson on entropy for college level thermodynamics. I wish you all the best and peace.